Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, Srinivasa Ramanujan's exploration of mark theta functions, documented primarily through his letters and notebooks, culminated in a formal presentation in 1917. This essay undertakes a critical examination of those functions, dissecting Ramanujan's claims regarding their properties, behavior, and relationship to ordinary theta functions. We will proceed through the work's implicit structure, evaluating the validity and significance of its core assertions. Section 1 Introduction to mark theta functions and Ramanujan's initial assertions. Ramanujan introduced mark theta functions as functions that, while analytic, exhibit peculiar modular transformation properties. Specifically, he asserted that as a mark theta function approaches any root of unity, its behavior closely mimics that of a modular form, specifically a theta function. The difference between the mark theta function and this imitating theta function would remain bounded. He initially identified several functions possessing this characteristic, classifying them into orders 3, 5, and 7. The primary claim in this foundational section revolves around the very existence of these functions, and their distinct behavior compared to both ordinary theta functions and other known analytic functions. The validity of this claim hinges on the confirmation that these functions possess the stated boundedness property under modular transformations, a property that defied easy verification at the time due to the function's unusual nature. Early skepticism among mathematicians arose from the lack of a rigorous definition and the apparent ad hoc nature of their construction. Section 2 Analysis of third-order mark theta functions. Ramanujan's list and identities. Ramanujan presented a list of 5 third-order mark theta functions, denoted with names like f of q, phi of q, psi of q, chi of q, and nu of q. For each he provided numerous identities. A central claim here is the interrelationship of these functions, expressed through these identities, for example, demonstrating how one function can be written as a combination of others, perhaps with ordinary theta functions included, or transformed into an equivalent form through manipulation of Q-series. Critical analysis of these identities requires reconstructing Ramanujan's reasoning, often relying on Curve-series manipulations and transformations he implicitly employed. Verifying these identities involves rigorous application of Q-series identities and modular transformation formulas. Discrepancies in early reconstructions highlighted the challenge in interpreting Ramanujan's often compressed proofs. An additional implicit claim is that this list is in some sense complete, at least representing the fundamental third-order functions. Modern research has expanded the known number of third-order mark theta functions, suggesting that Ramanujan's initial classification, while pioneering, was not exhaustive. Section 3 Examination of fifth-order mark theta functions focus on the alpha and beta functions. Ramanujan identified 8 fifth-order mark theta functions, categorizing them broadly into alpha and beta types. He presented identities for these also, many of which related them to infinite products and other series expansions. A key claim in this section centers on the specific forms of these functions, and that their series representations converge under prescribed conditions to analytic functions. Further, he implicitly claimed that these functions exhibit the defining mark theta behavior, i.e. boundedness near roots of unity when adjusted by a suitable theta function. Proving convergence and establishing this boundedness presented technical challenges. The analytical tools available in 1917 were insufficient to provide fully rigorous proofs for all claimed relations. The difficulty arises from the intricate interplay between the rapidly growing terms in the Q-series and the subtle cancellations that would be required to maintain boundedness. Many modern verifications rely on advanced techniques developed well after Ramanujan's time. The section's implicit argument is the utility of these functions in number-theoretic exploration, a prediction that would ultimately prove correct Section 4. The enigmatic seventh-order Mach-theta functions, a deeper dive into convergence and transformations. The seventh-order Mach-theta functions, only 3 in number, present the most significant analytical difficulties. Ramanujan's notes on these are sparser, and his justifications less complete compared to the third and fifth-order functions. The primary claim here is the existence of these functions as meaningful mathematical objects. This assertion hinges on the convergence of their defining series and their adherence to the Mach-theta transformation properties. Demonstrating convergence for the seventh-order functions proved considerably more difficult. The series involved exhibit even more subtle convergence behavior than those of the fifth-order functions. Critics pointed to the lack of explicit modular transformation formulas and the seemingly arbitrary selection of terms in the series as reasons to doubt their true Mach-theta nature. Contemporary work has shown that these functions do indeed possess the required properties, confirming Ramanujan's intuition, albeit through methods considerably more sophisticated than those available to him. One implicit claim concerns the profound relationship between seemingly unrelated areas of mathematics, highlighted by the unexpected appearance of these functions. Section 5. Properties near roots of unity. Ramanujan's asymptotic assertions and their verification. A recurring theme in Ramanujan's work is the behavior of Mach-theta functions as the variable Q approaches a root of unity, often expressed as an exponential involving 2 pi times I, where I is the imaginary unit, divided by some integer k, for values of k greater than or equal to 1. Ramanujan asserted that near these points, Mach-theta functions exhibit behavior similar to ordinary theta functions and modular forms. This is perhaps the defining characteristic of a Mach-theta function. He provided asymptotic formulas, estimating the function's value as Q approaches these roots of unity. The correctness of these asymptotic formulas is paramount to the validity of his classification. Verifying these formulas requires careful analysis of the error terms in the asymptotic expansions and proving their boundedness. This task becomes considerably more complex as the order of the Mach-theta function increases. Initial attempts to verify Ramanujan's work were often thwarted by the difficulty in obtaining sufficiently precise estimates for these error terms. Modern approaches use techniques from analytic number theory, including the circle method of Hardy and Littlewood, to rigorously establish the asymptotic behavior. The implicit argument from this section is that the seemingly irregular behavior of Mach-theta functions conceals a deeper regularity. Section 6. The connection to ordinary theta functions. Ramanujan's decomposition claims and their significance. Ramanujan claimed that a Mach-theta function, denoted as a general function f, could be expressed as the sum of an ordinary theta function, denoted as a function t, and a remainder term, which is bounded as Q approaches any root of unity. This decomposition, f equals t plus a bounded function, essentially defines what it means to be a Mach-theta function. The claim's significance lies in elucidating the relationship to previously known modular forms. Verifying this decomposition requires explicitly constructing the appropriate theta function t for each Mach-theta function f and then proving that the difference f minus t remains bounded. This is often the most challenging part of analyzing Mach-theta functions. Ramanujan did not always provide explicit formulas for the theta functions he used, making the verification process akin to detective work. The correctness of this decomposition is essential for understanding the modular properties of Mach-theta functions and placing them within the broader context of modular forms. Contemporary mathematicians have developed refined methods for constructing these decompositions, providing a deeper understanding of the relationship between Mach-theta functions and classical modular forms. One implicit assertion is that this relationship is not merely superficial, but reflects fundamental connection within the landscape of Q-series. Section 7. Ramanujan's methodology, intuition versus rigor and the challenges of reconstruction. Ramanujan's approach to mathematics was primarily intuitive. He often arrived at profound results without providing detailed proofs or rigorous justifications. In the case of mock theta functions, his methods involved clever manipulation of series, insightful observations about their behavior, and a deep understanding of modular transformations. However, his lack of formal proofs presented significant challenges for mathematicians attempting to verify his claims. Reconstructing Ramanujan's reasoning often requires filling in gaps in his arguments, providing rigorous justifications for his assertions, and correcting minor errors. This task is made more difficult by the fact that many of his ideas were recorded in notebooks without any accompanying explanations. The absence of explicit proofs forces mathematicians to rely on their own ingenuity and knowledge of related areas of mathematics to reconstruct Ramanujan's thought processes. While his intuitive approach led to groundbreaking discoveries, it also made the verification of his claims a long and arduous process. His work, despite its lack of explicit rigor, has proven to be remarkably robust, testament to the depth of his insight. The implicit claim here is that the exploration of uncharted mathematical territory benefits from both intuition and rigor, with each playing a crucial role in the advancement of knowledge. Section 8 Subsequent developments and the broader impact of mock theta functions. Following Ramanujan's work, mathematicians continued to investigate mock theta functions, driven both by the desire to verify his claims and the potential for new discoveries. The early work of G.N. Watson, Atul Selberg, and George Andrews played a crucial role in establishing the validity of Ramanujan's assertions and developing a more rigorous theory of mock theta functions. Subsequently, mathematicians have found applications of mock theta functions in diverse areas of mathematics and physics. These include combinatorics, representation theory, string theory, and black hole physics. Their appearance in such disparate fields highlights the profound and unexpected connections that often arise in mathematics. The discovery of new mock theta functions and the development of new techniques for studying them continue to be active areas of research. The theory of mock modular forms, developed by Sanders Wedges, provided a powerful framework for understanding the modular transformation properties of mock theta functions and relating them to holomorphic modular forms. The impact of Ramanujan's work on mock theta functions extends beyond their specific applications, influencing the broader development of number theory and related fields. The implicit argument is that the exploration of seemingly esoteric mathematical objects can lead to profound and unexpected consequences. Section 9 Reception and revision of Ramanujan's ideas. A historical perspective. The reception of Ramanujan's work on mock theta functions was initially mixed. While some mathematicians recognized the genius and originality of his ideas, others were skeptical due to the lack of rigor in his arguments and the unfamiliar nature of the functions themselves. The verification of Ramanujan's claims required significant effort and the development of new mathematical tools. Over time, as more of his assertions were proven and the applications of mock theta functions became apparent, his work gained wider acceptance and appreciation. Subsequent revisions of Ramanujan's ideas have focused on providing more rigorous proofs, developing a more comprehensive theory of mock modular forms, and extending his results to new classes of functions. The historical trajectory of Ramanujan's work on mock theta functions reflects the evolving standards of mathematical rigor and the increasing appreciation for the power of intuition. The initial skepticism gradually gave way to widespread admiration and recognition of Ramanujan's profound contribution to mathematics. One implicit suggestion is that the value of mathematical work is often judged not only by its immediate utility, but also by its long-term impact and its ability to inspire new avenues of research. Section 10 Conclusion. Enduring significance and future directions. Ramanujan's work on mock theta functions stands as a testament to his remarkable intuition and profound understanding of mathematics. Despite the lack of formal proofs and the initial skepticism surrounding his ideas, His assertions have proven to be remarkably accurate and have led to significant advances in number theory and related fields. The theory of mock-modular forms, developed in the decades following Ramanujan's death, provides a rigorous framework for understanding the modular transformation properties of mark-theta functions and relating them to classical modular forms. The applications of mark-theta functions in diverse areas of mathematics and physics highlight the unexpected connections that often arise in mathematics. Future directions for research include the discovery of new mark-theta functions, the development of new techniques for studying them, and the exploration of their connections to other areas of mathematics and physics. Ramanujan's legacy continues to inspire mathematicians and physicists, demonstrating the enduring power of original ideas and the importance of pursuing mathematical exploration, even when it leads into uncharted territory. The legacy of Srinivasa Ramanujan's mock-theta functions lies not only in the specific mathematical objects he identified but in the enduring inspiration they provide for mathematical exploration across diverse realms of thought.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.